Good morning, everybody. Welcome to this second hackathon for the BETTER project. Today is the hackathon related to the GeoInt challenge domain. We can actually already start with the first slide just to give you a little bit an overview of what we're going to do today. As I said before, maybe not all of you were present. For the first part of the meeting, you will be mute. In any case, you can write in the chat here or in the Google Meet link for any discussion. Possibly, if the Google Meet will be more dedicated to a technical discussion, if you are stuck in some steps or you want to add some more technical question. We will be approximately a number of 10 people, so it's a good number to have a sort of interactive discussion for any issue that you want to go into depth. So I will start the procedure to make me a presenter. See 1 second, where is my Can you see my screen now? If you can nod with the head or
we see the Meet chat, Michele.
Now you see the
now the presentation.
Yes,
okay,
correct.
Perfect.
The slides link is also shared in the chat.
Okay, thank you for the support, because you have many windows open. Okay, so let's put it in presentation mode. Point this. Okay, can you see also the chat in the screen or just the presentation?
No, it's okay, yes, the presentation.
Perfect, okay, because I see both. Okay, so welcome everybody. This is the second and final hackathon for the BETTER project. Today, as I said, is the turn of the Geospatial Intelligence challenge. It will mainly based on the procedure to detect changes with the SAR images, and then also there is going to be a part, let's say called analyzing and post-processing. So we will have you will have more information later on, but the idea is to give you a sort of a brief introduction on SAR data. I know that maybe some of you already have a lot of experience on SAR, but it's going to be, let's say, shorter or longer this part with respect to the knowledge that you have. So the idea is also try to know each other better to understand if you are familiar with some concept or not. And the second part is more about explaining you how you can work with SAR images, applying change detection techniques, or try to, after you have a map of changes, you can improve the interpretation of the image for your analysis. So, as I said, the first part will be a sort of introduction to the project. I don't know if you're familiar with the BETTER project, but we'll give you some very few information on it and our challenges that we are managing here at SatSen. After this, in my presentation, we would like to have a sort of tour the table, just to know, as I said, more or less if you are familiar with SAR or with Sentinel data, with the processing, and in order to speed up or less with some specific part of a hackathon. Then I will pass the word to my colleagues, Omar and Adrian, that are today they are staff of SatSen, and will be in charge of a presentation of exercising. The exercising are we were wondering how to create this kind of hackathon. If you wanted to do something like more step-by-step or something like more open exercises, we decided to go to a sort of step-by-step exercises because I think also considering we are in a sort of online environment, it's better to have this kind of structure to also maintain the attention of you, of the audience. In any case, you have all the exercise, you already see the link on your own. So if you think for you something's very easy, you can ask us to speed up or to go directly to the second exercise. We're going to explain normally the exercise with this structure, explanation of the task. We'll show the step to perform it. And for some of the exercise, there is also more, let's say, a hackathon part. So you'll have you've been asked to do some steps on your own. At the end of the exercise, we would like to have a sort of open discussion. Of course, this hackathon has been organized for mainly to let's say, to give you a sort of feeling of what Better is and to play with the images. So please interact with us if you need some if you want to know something more about any step or anything will be like presented today. Briefly, I'm gonna present you, so I'm gonna give you a sort of introduction of sorry, I'm gonna give a sort of introduction of the SatSen. We are an agency of a EU Council. We are basically responsible of the, sorry about that. We have too many windows open and I have some issue with the we are an agency of the EU Council. Our mission to support the decision-making action of the European Union in the field of common foreign security policy. What we are doing basically is analysis of satellite images and other collateral data. We are based in Torrejón de Ardoz in Spain, close to Madrid. We are, as I said, providing joint products based on analysis of satellite data. We don't own our satellite data. We use mainly commercial satellite, very resolution from SAR optical, and we recently introduced also the use of open data like Sentinels. And what we do is creating this product for our stakeholders, who are mainly composed by the member states of the European Union and other EU entities or international organization. In particular, this the unit involved in this project is the RTDI unit. RTDI stands for Research, Technology Development, Innovation, and we are basically try to improve the capability of the center, tackling the whole Earth observation and collateral data life cycles. If you are familiar maybe with our unit, you see us working on a different project regarding like data acquisition system, like apps, secure sat communication, YouGov.com. We have like better project in the innovative technology like big data, artificial intelligence, and we are also working on developing our own chain based on Earth observation data, like SAR change detection, like you will see today. And a big part of also our work is maintaining and establish cooperation with entities like ESA and GEO and other entities in the framework for H2020 project. Better is a project, H2020 project funded by European Union. As you see, it's we are almost at the end of the project. It started 3 years ago. The idea of Better, it's like implementing a Earth observation with data layer to exploit the use of European Earth observation data, in particular Sentinel, trying to respond to the needs of the user. The idea of this project was to create, with the support of the technical partners, some big data challenges to answer to some big data challenges through data pipeline, let's say, to try to solve the issue of 3 main domains. One is the Geospatial Intelligence. Then there is the workflow program with the food security and the GeoHazard community with the ETH Zurich. The idea is that during each year of the project, each promoter, each community has introduced 3 challenges, and plus there are also challenges brought by external communities. So let's say that to summarize, during the project, 36 challenges have been, let's say, solved. A challenge normally it's generated by the need of a community to process a big amount of data. That's why also this project is related to the data call. And normally the use of resources is not owned by the challenge promoter. That's why BETTER helps us in the processing of the data, in the creation of infrastructure, so the user can focus only on the final step, the analysis of the data, of the results. So the data are brought by the technical providers to the user, they are processed, and then there is like the analysis and the output generated for the user community. Especially for SatSen, the challenges generated are part of the Geospatial Intelligence domain to solve some issue of a space security community. Just to give you some example of our challenges, the number that you see here basically are the 3 years of a project. We have, let's say, 3 teams, which is change detection, thematic indices, and end user, and we try to develop processing chain related to this specific teams, let's say. The first one, the change detection, was mainly based on SAR with Sentinel data. If you're familiar with Sentinel, processing of Sentinel acquiring IW mode or stripman mode, already processing level 1 as GRD. When we also work with Sentinel-2 data in the optical domains for creation of water and vegetation indices, mainly to, let's say, create some application related to the space security domain, like it can be illicit crop or mineral indices, illegal deforestation. And the last year, which is this one, we mainly focus on fire. So we try to create some indices, thermal indices, using the shortwave infrared band of Sentinel-2 to identify some burn area. A few words about Sentinel, then my colleagues also will talk more about this during the hackathon. You probably know Sentinel-1. It's very interesting for us. The Sentinel-1 was not a satellite, let's say, created for the security domain, but we actually found it very useful because it's our work is mainly based on the interpretation of very high resolution images, while Sentinel can be considered a sort of middle high resolution, maybe if you talk about street map. And it can be very useful because with respect to very high resolution data, it's actually free. You have a high revisiting time, and regardless of weather condition, but this is a big characteristic due to the SAR sensor, and it can be used to monitor a very wide area. Of course, you cannot see everything related to space security with the Sentinel, but the idea is like to have a sort of wide monitoring with Sentinel data, and then when you spot something interesting for you, you're gonna acquire very high resolution images to have like a better detail of what you need. I will show you just 2 images to introduce you to what we're going to do later. For instance, this is a Google Map image and the related Sentinel-1 image, which show you what you can see with the Sentinel. For instance, here you can see clearly from one image to another the construction of some sites, and now they look like in the SAR images. Of course, also the color coding will be answered later. Just now, it's important that you notice that in the image respect to another, there is a sort of change in the color. It looks like there is something has been going on, something has been built, and it takes like a sort of expert eye to identify exactly what. But in any case, the important concept is you can see something with the Sentinel data with respect to the construction on your site. Changing infrastructure is actually one of the main topics in the space security domain. Time series also here is you can see it's very useful. Here is an island, Charpia, located in the Indian Ocean. I think it was really talk in the news the last couple of years because they're constructing a refugee camp. You can see the evolution of the island in terms of tide. It's an island subjected to like flooding, and also the evolution of the island with respect to the construction of a refugee camp. You can see the drainage channel, especially in the last image. You can see the houses, and you can see also an increase of boat traffic close to the island. And this is something obtained with Sentinel-1. We have also an exercise on this topic later. So last two slides before starting to code. I think this hackathon is very important for a participant, for you, in order to discover better in a sort of interactive way. So seeing what we actually do practically with our pipelines, with our processing. You will learn more about the Sentinel-1 image processing, change detection, and the post-processing techniques. And the idea, as I said at the beginning, is a sort to have an interactive session to share knowledge between you and between us, of course, because there is always something that we can learn more. For better is very important because it will increase awareness of infrastructure on what we, the technical partner in particular, did, and to also to collect feedback from additional user on the solution we develop. And again, also for SatSen to have like to get new idea from you, from a new points of view for our challenges. I conclude to my presentation. Thanks for listening. Now it's time to do like the real part of the hackathon. You already received a link in the email. If you didn't receive it, there is here the link of GitHub repo. And now I think it would be nice if to have a sort of, as I said before, to tour the table, just to understand your level. If you want to say something about the, if you know already SAR data, if you know already Sentinel, it will be helpful for us to know if you can speed up or not in some specific topic of the hackathon. Thank you.
Sorry, yes, before going to that, I was just willing to mention that if you could open already the repository from the exercises, and there are two options. The more natural one is to just click on the launch binder link that you see on the repo.
Again, perhaps you can share your screen to show it.
Okay, yeah, sure. Let me very fast share my screen. It's in order to speed up the process because it takes some time to build so this technology is quite nice. It allows you to run. Are you seeing my screen already? Hello?
Yes, we can.
Okay.
Yes.
So yeah, this is the repository, and there's everything is explained here. But as you see, there are two options to run the notebooks locally. So you need to have a already installed Docker. So it takes a bit more time. It gives you, let's say, the advantage to be able to use your own resources. But the more natural way is just clicking on this launch binder icon. When clicking, it will start preparing the repository for you. Sometimes it takes more time if it doesn't find the image in the local deployment where this is done, and you will end up with something like that. All the repository already built in a Jupyter Lab environment. It's very fast for me because probably it has already the Docker image cached. But if you could already launch it so that we are all set up after the tour the table, it will be nice. So yeah. Now I think we can already proceed to the table. Thank you.
Okay, I just want to ask you, okay, the webinar, the hackathon will be recorded. I just want to ask you if you have some problem with that, about the recording of it. If in case you have some issue, please write in the chat, and or tell us directly here, or separate in a separate channel. I think now you are able to talk. So if you want to just introduce yourself very briefly, just a few seconds, just to tell us if you are familiar with SAR, and Sentinel and this binder environment. So just to understand if you can speed up or not some topics.
To Sentinel-1, Sentinel-2 data, because we will be like just very briefly commenting on the different characteristics of those two satellites that are, by the way, free and open data. So you can already access it on your own, and we will show here how to do it very briefly for those of you that have not done it before. Also, just to mention, it's important to mention that here we have a limited time and limited resources in this environment. It's this binder system. So we will be, for sure, during BETTER project, we were using a different approach, as it was mentioned before. BETTER proposes this big data intermediate service layer so that we don't need to actually focus on this, what will be described in this first introduction. So we don't need to focus on how to access the data, how to download it, and so on. We can already rely on better capabilities and to orchestrate and to provide cloud appliances to process the data following guidelines or following the challenge description that we make, the challenge promoters make. And then we can focus on what will be shown mostly on the second part of the hackathon, on the last notebooks, on just the exploitation of this analysis ready data. But we will go through step by step through the different phases. So I hope you were able to launch Binder, and maybe for some of you is still building. It depends on where the system allocates the resources and if the images are already, let's say, accessible for you there. If not, this one I think you can follow with me. There's no need for you to do it. There's no specific exercise associated to this. But of course, if you have trouble with starting Binder, we have people around that can support you. So please raise your hand and at any moment or just speak and let us know that you are having some trouble. So again, this first exercise, we will see the two main sensors that we have been using in our challenges in BETTER are Sentinel-1 and Sentinel-2. They have different characteristics that are, some of them are described here in this section. So Sentinel-1 is a constellation of two satellites, Sentinel-1A and 1B. It's a C-band synthetic aperture radar, SAR. We'll later on discuss a bit more about SAR image formation and so on for the ones that are more interested on that. An important part of this sensor is that the collection, it can perform collection of data in all weather conditions. So when we will see later that when we see optical data, like we get with Sentinel-2, it's affected, for example, by clouds. So if there is an area which is covered by clouds in a specific moment, we will not be able to see below, no? But with Sentinel-1, we can. The spatial resolution depends on the type of acquisition. There are different modes of acquisition, but it can go down to 5 meters spatial resolution, and it has swaths of up to 400 kilometers. So it covers wide areas in a single swath. The orbit is sun-synchronous near polar, and it has around, it depends on the place of the world, but it has around 12 days repeat cycle. Related, in comparison with Sentinel-2, is also a constellation of two twin satellites, 2A and 2B. It's multispectral data, so it has 13 bands. Not only the optical part of the spectrum is visible, it's also on the near infrared and shortwave infrared. We will not be discussing that much in this hackathon about Sentinel-2 because our main interest today is on Sentinel-1. But we have, in general, in our different challenges, we have been using both Sentinel-1 and Sentinel-2 to fuse this information and to have, let's say, a more complete picture of the challenges we were addressing. With regards to the resolution, it's depends on the part of the spectrum we are taking a look, but it goes from 10 meters to 60 meters, and it has 290 kilometers of field of view. It's also sun-synchronous orbit, and it has revisit times around 10 days with 10 days under the same viewing angles. So here, just going into the more like the coding part, I mentioned it here above. You have a link in the directly on the notebook to SciHub. So SciHub is one of the data hubs, let's say, where you can have open access to this data that we will be seeing today. As I mentioned, in BETTER, we are not focusing on this, and the technical partners are making sure that we already have analysis ready data, so we don't go to the raw data that you can find there. But we believe it is important to show you, so that in case you want to repeat this exercise later on, or you want to to do your own analysis, there are different places to get it, but this is definitely the easiest way to access Sentinel data. So the first example we will do is just to search and preview some imagery of those we mentioned above. I'm installing some dependencies here. Sorry, it's first. If you see at some point that Jupyter Notebook is not executing, it's probably because I automatically shut down your kernel. So just go in here to the top for the ones that are not familiar with the Jupyter Notebook and Jupyter Lab environment. You can just select the kernel. We have prepared most of the dependencies on this BETTER kernel, but there are some specific ones that we are installing here. And it's also, we decided to keep them here so that you are also aware of what kind of libraries you can use to access, to visualize this data, etc. Of course, you can also refer to the documentation and go to the environment, which is configured, etc. So here I'm installing Sentinel Sat is a library to accessing open search catalogs. In this case, we will be accessing the SciHub site with this open search, and some libraries for working with vector data and raster data, and also to print nice maps. No? So here we are, let's say, we will focus on a small area of interest that we decided here on the port of Malaga. You can see how easy it is to represent data in this Jupyter environment. I have already an account. You can already go to the SciHub and register yourself, but I have already an account that we can use to search for some data. And you can see it's very easy to define a range of dates and define a query to Sentinel-2 and Sentinel-1 data, and submit it to the open search interface. And you have, for this range, period range that I specify here, you have 2 Sentinel-1 images and a Sentinel-2. You can see that they have different properties, etc. For example, the cloud cover is something interesting. As we were mentioning, Sentinel-1 is not affected by cloud, so it's let's say not provided in this product, while for Sentinel-2V data, it is provided as a percentage, so it's not very much covered in cloud, this image, in fact. If we represent just the footprint of those images here on a map, we can see also some differences. No? So we see, we have our area of interest, which is way down here, small area of interest, and we can see how the Sentinel-1 products that we found look like. So we see that there is a descending path here and an ascending path here, and we can see also the extent that they cover. No, when we compare it with Sentinel-2, we see that the product it's squared because there is some pre-processing before that it's making it fit to this grid, no? And the stand covered by the product is smaller. So one thing that was mentioned before during the tour de table was that it was somehow a bit more complex to process Sentinel-1 data. One of the reasons for that is maybe the size and the type of content of the images that make them heavier. No? Here I'm just filtering, so we see a preview of 2 products that are exactly on the same date. I selected this date by looking at the metadata of the files here. So just by filtering to those and to have a first, let's say, view on how this data look like, it's you can see already. Let's do the same here. You can see how Sentinel-2 data, as I mentioned, it has is multispectral. So we are only focusing here on previewing the visible part of the spectrum. So it's basically what you will expect to have in a photograph, no? And this is, or with your own eyes, and you can see already some clouds here, no? While if we switch to Sentinel-1, you can see already that it's a bit more, let's say, strange or difficult to interpret. This is also a color composite using the two polarizations of this image. This is the typical way that previews are shared in this sensor. And we will explain later on a bit more about the image formation and what does it mean, the bright spots here on the not so bright spots in some other places, or why we have bright spots here on the peaks of the hills or of the mountains, etc. And just to have a bit of a taste about the resolution, you can see here two images of a different area. This is the airport of Madrid Barajas. You can see here an image not affected by clouds, and the problem that we were mentioning before about the clouds, and just to have a sense about the resolution, which in case of Sentinel-2 is 10 meters. You can see more or less how it is. So I don't know if we want to proceed with the exercise, but I think it's not something very complicated. So it's for the ones that are not very familiar with accessing this kind of data, it can be useful to do it later on after the hackathon. You can just create an account on this SciHub site, browse a bit the documentation of the library we use to perform search against this endpoint, and maybe you can just visualize some data on the place you live and use some of the code above to do it. So I would say that we can, since the focus is on SAR, I will give the floor to Omar, who will give us more details on SAR image formation, etc. But of course, if you have some questions, or if you prefer to really perform the exercise, please let us know, and we will stop and give time for doing it. What do you think?
Go with the next notebook. As Adrian has told you before, it is not important to run all the things in the notebook. This was most a demonstration one, but perhaps if you can go to the introduction notebook from Adrian and to run at this cell, so we can install all the things, because there are some dependencies that perhaps you are going to have some error later in the processing. In any case, if not, you can only copy this line. If you at some point you have an error about a dependency is missing or something like that, you can try to copy this line and execute it in copy paste in other notebook and execute it. I think it's only this. Okay. So basically now we are going to try to make a short introduction of SAR, and basically is to try to understand how the images are generated and why we are looking at them like we look at them. So basically is how the SAR work. It is quite different to the optical sensors. In optical sensors, in fact, the sensor only have a receiver, so the light from the sun reflects to the terrain and goes to the receiver. In this case, the SAR is launching its own energy, a beam of energy, and he receives the echo. So taking this into and the SAR, the name is synthetic aperture radar. So this is because it is a technology in order to be able to improve the resolution by making by the motion of the radar antenna. So basically, what the SAR is doing is, this is the satellite. He's going to launch beam of energy, and he's going to receive the echo. So what we are going to see is the backscatter of this beam. So the problem with that is that it is possible to have a lot of different geometric distortions. For example, if you see at this part of the image, when we have a very high slope in the terrain, it can happen that, for example, we can launch a beam here and a beam of energy here, and we are going to receive this before this one, because if it is closer to the satellite. So in the common geometry used in the SAR is the slant range, we are going to see this point before this point. So we are going to see the image completely distorted. And also, because of this geometry, for example, in this case, all this part of the terrain is not going to be possible to see anything because no beam of energy is going to go to here because and we are going to see a shadow in this part of the image. So we are going to see the images that are not completely similar to the things we see in Sentinel-2 or other optical sensors. So basically, the important thing also is that the pixel values are going to be proportional of the energy received. So, and we call this the backscatter. So we are going to work mostly today with the backscatter of the SAR images and to try to understand the images. So how this geometry and how it is working the SAR affects to the interpretation of the images. So depending on the terrain, we are going to see different things. For example, for water, there are regions with in the regions with calm water on a smooth surface or a flat terrain, we are going to have mostly a specular reflection. I have another image here. For example, here we have a flat terrain. We are going to launch the beam of energy. It's going to reflect away, something similar to a specular reflection. So in this case, we are going to see very black pixels because there is no energy received by the SAR. If the route of the surface is increased, we are going to have some kind of reflection, like for example this is going to be to launch away some part of the energy, but we are going to receive some echo. So depending on the roundness, we are going to have also a different backscatter. Also, depending on the slopes, as we have seen before, we are going to be able to receive a lot of backscatter, no backscatter, on depending of the slope is positive or negative. It's going to affect to the backscatter. And also, regarding the man-made structures, we are going to receive a very big backscatter because of the double embossing. For example, in this image, you can see what is the double bounce effect. Is the beam of energy is going to reflect in the terrain. It's going to be reflected again, a double bounce in the building or the other man-made structures, and we are going to receive a lot of backscatter in the SAR. So, for example, in this image, we are going to see that this is a part in the coast of Australia, and we see the sea. We have a very black pixel, so we don't receive any backscatter. Also in a river, so it is quite easy to identify the rivers or the sea. Also, if we have some island or some ships, we are going to see points with high backscattering, so it's going to be easy also to detect. And regarding the slopes on mountains and things like that, we're going to see that depending on where is the SAR, we are going to see one face of the mountain with a very high backscatter and the other one with very low backscatter. For example, here, in this case, the image is, we have the SAR, the satellite from here. He's launching the beam of energy from this side. So all this face of the mountain, we're going to have a very high backscatter, but all this area is going to be a kind of shadow. So we have these black points in the black areas in the image. So we start here another dependency. Normally, if you have, I have also, I don't know if you're having the same behavior or not, but sometimes the kernel is slow. So you have to select here the better one. And we start from the beginning. So now we are going to try to see some examples of images and to understand what are we looking at. So I would like to, in this part of the exercise, I would like to, if possible, if you can unmute some of you and to discuss what are you seeing in this image. For example, in this image, what kind of things do you see? For example, what do you think is this? If someone wants to scatter, you can say it could be vegetation. So not a very flat terrain, because if not, we will see like that. This terrain will be flatter than this one. So as you see, it's not as evident probably to an RGB image from Sentinel-2 because we are more used to see in the Sentinel-2 images. Mostly when we use the true color, we see what we are used to see with our eyes. But in this case, we have to think in a different way to try to see what are we looking at. Also, this is another example of Niamey, the city of Niamey. And I think it was interested, this image, to try to see, for example, this is a zoom in the city. So we see these are all pixels that are saturated. So we have the very high backscatter, in this case, all the white pixels. And we can see the roads, for example, they are going to be flat surface with a specular reflection. So we can also identify the roads. So in this case, the big roads, because of the resolution. If we have a SAR with a higher resolution, we will be able to detect more streets from inside the city. And also, I don't know if you can have an idea of what is this kind of a structure. This data, and it's going to be downloaded and show directly from your notebook. But also, if there is any issue with that, we have also upload these images to another channel. So if one of you have any problem with accessing these images, tell us and we can share the other links with you. But in any case, what we are doing in the code here is only to, okay, we define which is the image we want to see, the area of interest. We are going to download or to use some images for download it only the images in the area of interest that we have indicated. And this is a function we have defined for visualizing the images. All these functions also, and in your, if you are going to develop some of other functions in the future exercise we are going to propose, you can do it in the helpers. So this is only a collection of some common functions that we are using from some of the notebooks we have. So if you have any doubt about some of the functions we have here, you can look at the helpers, and also for developing your own if you want to change something. So in this case, this image is Charpilla. This is the island of Charpilla. And also, I think that, I don't know if you were Basque or one of your colleagues who introduced before that you were working on ship detection. For example, we can see in this SAR image that we have a lot of ships here. So the ships are very visible in SAR images because they have a very high backscattering with a background in a very black, that it is the sea. So in this case, we can see the island. We can see here, this is the continent part close to Charpilla. We have seen that we have some urban areas here. Probably this is the port with all the ships parked here. And also we can detect some kind of activity. We are going to see later this data set with the construction of the refugee camp here in the island. And he's starting to go some ships here. We can see one ship parked here in the island. So this is the moment where they were the starting point of the construction of this refugee camp. So in this case, okay, I had it chatted before, but it is now that it is downloading the data. So this can take some seconds or minutes to download and visualize the data. And an important thing is regarding these SAR images is that, as Adrian has told you before, you can download it from SciHub. But when you download them from SciHub, you are not going to see, and you visualize it with any software with like QGIS or Snap, something like that. You are not going to be able to see them directly like we are seeing it like here. In that case, this image, we have made a pre-processing. The pre-processing is going to be different if we are using Sentinel-1 images that are SLC or GRT, that are the two main images from level 1 that we can download from SciHub. The difference is in the SLC, there are images in a slant range geometry. So we are going to have, again, all the distortion of the geometric distortion that we produce with the image fold over or the shadows. And the GRT are images that are already projected to the ground, but they are projected in an with an ellipsoid, so they are not taking in account the digital elevation model, so there are some missing information and geometric distortions still. And also, why are we using sometimes SLC instead of GRD if they have already some preprocessing? Is because in the SLC we have also the phase information. So depending on the analysis we are going to do, if we are going to work only with the backscatter of the images, we don't need the phase information. The phase information is when we have the beam launched by the SAR, we are going to receive the echo. This is the amplitude of the energy received, but also the phase. The sensor is going to create this beam of energy with vertical polarization. Sorry, no, this is another thing. We are going to launch a wave, so we are going to receive this wave with at a different point with a, I don't know if you know what, we have the wave here like this. We can receive it with the phase at this point of the wave. So this is important because with this we can see also which is the distance, for example, of the point, and we can start some information for making some interferogram analysis or things like that. So if we are going to work with this kind of operations, we need the phase information, but for analyzing the backscattering, it is not needed. So in this case, we will go for the GRD. And also there is the preprocessing can be very different depending on the application, but usually this is this kind of preprocessing that we are applying, to apply the orbit file, to improve the geolocation of the images, to remove the thermal noise, the border noise, the speckle noise with the speckle filtering, to calibrate the images, and to make the terrain correction in order to have the digital elevation model and not only a flat ellipsoid model for doing that. And then we convert to decibels or to byte or to float the output we want to show. So usually this preprocessing is made using software like, for example, Snap. I don't know if you know Snap, but it's usually standard. This is the toolbox for the Sentinel missions. And it is important to know how this preprocessing is made because the output of the images can be different. For example, I don't know if you have noticed it, but in the function we have here for visualizing the images, basically here I'm visualizing SAR images, but in this case, in the NIAME image, for visualizing, I am introducing here the mean value and the max value I want to visualize. In this case, it's between 0 and 255. And in this time with Charpilla is between 0 and 0.5. So in fact, we are seeing backscattering, but the range of this value of the backscatter is completely different. So it depends on this last part of the preprocessing, which is if I have converted the value of the pixel or not. Normally, in SAR images, it is basically we're working usually with float, but sometimes we're converting these values to byte in order to visualize it better, to save space in the disk. So, sorry, it is important to know which is the final conversion made to the data. And if we are trying to make this conversion of the data, we have to look some points in detail. So, for example, which are the minimum and maximum values that we want to be represented in the images of the final image. Also, it is important to know if we need to recover the original values. For example, here, this is the original values of the backscatter, so we can use it as input for another processing. But here, I have converted them to byte. So I don't know exactly which is the amplitude of the backscatter, we can say, because I am only representing my data between these two values in order to have a good stretching for visualizing, but I cannot recover the original value. So for example, if I want to compare this data with another image at the same date, at the same area, but at different date, we cannot compare it completely because I'm not sure if the conversion to byte has been made in the same way or not. So I should recover the original values to be able to compare time series of data. Also, it is important to assign which is the min and max value for the new data that we got. For example, in this case, the backscatter can go from 0 in the sea, and we have a backscatter of 10 or 20 or more, even more in some pixels in the city, because they have a very, very high backscatter. But if I try to represent this range between 0 and 10 from the float in a byte, perhaps I'm going to lose a lot of resolution, because most of the pixels are going to be between 0 and 10 in byte, and the 10 bit and 255 are going to have only pixels on this. I'm going to show you this in an example later. And also about the accuracy, for example, for this data conversion, perhaps if I need more accuracy, perhaps to change to a byte, I'm going to convert to int 16 or things like that. So having these values, the float or int, are going to have advantages or disadvantages, and depending on the final application, we have to understand which is the best value for our results. And if you want, I'm going to propose an exercise now, is to convert the pixels from Charpilla to byte. So to make a fast function to convert we have these values here that are values, I'm representing the values between 0 and 0.5. And imagine that I would like to convert this to byte and to visualize these images. So if you want, maybe, I don't know if you,
yeah, maybe one question to the attendees. Can you, were you able to launch a binder environment or have it locally prepared? Can you raise your hand, those of you that are able to execute the notebook that Omar is presenting? Okay.
But now we are going to see how to compute some more images and some visualization that can help to visualize this. So this is the changes we are looking at. Also, we have some examples in Charpilla. In Charpilla was the same. We have the data sets online, but also in local. In this case, I have in local the two examples I wanted to show you here, so it's going to be faster. So in this case, this is the image we have seen before, but at two different dates. This was from December 2017, and this is was September the year after. So we can see this is the island. We can see here a ship, and this is the island after 9 months. So we can see that they have constructed something here. They have constructed the refugee camp here. They have some activity in the port of the working things here. And also it is important because for this data set, there are two different things that we can analyze. First of all is the construction of the refugee camp, but also this area. In this case, you can see that we have a increase of the backscatter for the man-made for the man-made structures. And also here, in this part here, we have a decrease of the backscatter because also the island, and it was interesting for this dataset, was affected by floodings. So in this case, there are areas that have floods. So it is for this that they have constructed around the refugee camp some wall or some things to protect the refugee camp from these kind of things. So in this case, we can see two different changes: the floodings, and also the refugee camp constructions. And also in Niamey, this is the example we saw you before. We have here the Niamey, the area of Niamey Airport at 3 different dates: the January, June, and September 2018. And we can compare this with the very high resolution optical images that are available in Google Image. That we see that there is something that has been constructed here in one part of the airport, and there is perhaps an ampliation of the airport during these dates. So we can see also here. And also a tool that we are going to make this analysis visually is that when we put the images in parallel like that, we can see them, but it is not also very easy to, it's not always very easy to identify the changes. So what it is usually we use usually for doing this kind of visually comparison of change detection is to generate an RGB. So this is an RGB composite that we call the ACD, and it is composed with the 3 bands that are the RGB. The air band is going to be the backscatter before. Normally for the ACD we take two images, so we have the red band, the backscatter at the first date, and the G and B band we put the backscatter at the second date. So with this composite, what we can see is that we are going to see in red, there are things that they have high values in this band and low values in this. So they have the backscatter has decreased. For example, it corresponds to buildings that have been destroyed or that areas that have been affected by floodings, for example, there are new water bodies. So we have some backscatter at the beginning, and then we have very low backscatter. In cyan, we are going to see things where the backscatter has increased. We compare with the red, and so if this is higher than this, we are going to have a bigger backscatter at the end. It corresponds, for example, for new buildings. And in the gray scale, we are going to see things that are not have no changes. So if it is gray, it is because we have similar values in all the bands. In the gray scale, it could be black, so we have similar values and they have a very low backscatter before and after, or in white, they have a very high backscatter before and after. So if we visualize this, we're going to see that. This is the RGB plot, the ACD, between in NeaMaze. So we are seeing the changes between these two images. So we can see here the construction of new things here in the airport that corresponds to this part here. Also, we can see this new structure that it is building here. We can see it here. And also we can detect some kind of thing around here that it is some kind of building that has been destroyed, that it is something here. It's not very easy to look at it, but if you zoom in with Google Earth, we can see that there are some structure here that here is that not exist anymore. So sometimes we want to compare it visually. In this case, we can visualize them in parallel and to try to look for changes, but usually it is very more useful to work with this RGB composite for clearly highlight which are the changes in the images. So we propose here an exercise to generate RGBs with Charpilla or the Amazonas, but I think we can do it. You can do it by yourself later. It's only to use some of the images we have defined later, because I prefer to have more time for the final exercise where we can make a summary of all the things we are doing now, and we can come back to some exercise. So if you have you don't have any doubt about this notebook, you can pass to the next one. It is clear for you why this ACD is useful and how are the images that we want to compare. We are going to compare the next notebook about the changes in the backscatter of the two images. And now what we are going to do in the next notebook is to try to make it automatically by defining some thresholds or things like that.